Welcome, this is lecture number 19. In this lecture, we are going to talk about variable frequency control, and we want to understand what are the opportunities and challenges using variable frequency control. So, in this lecture, we are going to talk about what are the limitation of fixed frequency control. Then we will talk about what is the need for variable frequency control. That means we should be motivated to find out why do you need variable frequency control. Then we will discuss about ripple based control, some motivating case study, okay? And then we will also consider some MATLAB based simulation case studies and of course few experimental case studies. So, first we will talk about what are the limitation of fixed frequency control. Although point to be noted that still majority of the commercial product, power management commercial product are dominated by fixed frequency control, particularly when you go for high load condition, medium load condition, it is primarily dominated by fixed frequency control. But when it comes to light load, that means when you are talking about a power converter which has to be designed for a wide load current range, that means the load current can be a few milliampere or even in some cases maybe few hundreds of microampere, and it can go up to few tens of ampere, okay. So, such wide load current range, we will first see that fixed frequency control has a limitation when you go for light load, when the converter particularly operate in discontinuous conduction mode, because there we will find the switching loss will be dominated, as a result efficiency can drastically fall. And when many commercial products go for multi-mode control, that means they use some dedicated control during light load and probably they will prefer for fixed frequency control for high load or medium load. Then we will talk about current loop stability aspect under wide duty ratio operation. So, we will see the current loop stability can drastically get affected under fixed frequency control, and this will motivate us that we will also discuss about, that means in order to overcome the current loop stability problem, we will find out some method to stabilize, and then we will see if you go to variable frequency control, then you can have much I would say better degree of freedom in terms of stability of the current loop. Then the slot transient performance, in majority of the product, commercial product, the design of fixed frequency PWM control, whether it is a voltage mode or current mode, we still use small signal because we still derive transfer function, we still derive what is the gain crossover frequency, phase crossover frequency, then we design compensator based on transfer function, frequency response. And in future subsequent lecture, whenever we will go for modeling, we will see that such small signal model is not valid when we try to go beyond certain bandwidth. So, in this particular lecture, we will show some simulation case study that the response due to a small signal model and that using actual switching converter, they will start diverging when your critical crossover frequency you try to increase or the bandwidth you try to increase. So, here the slot transient performance is because of using small signal based design in fixed frequency control. So, now we talk about current loop stability scenario using current mode control for wide duty ratio range. So, first of all we have two solutions. The first is the peak current mode control. So, how does it look like? Let us consider let us consider peak current mode control, the waveform, control waveform. So, here we are going to consider the clock and this is a waveform, okay. So, if we take the peak current mode control and this is our clock. So, this is our switching clock, it comes, then again it comes like this, and this is our switching clock FSW, and then this is the waveform, okay. So, this is our reference current, peak reference current, and this is our inductor current, okay. So, in this control, this is also called trailing edge modulation. trailing edge PWM, because here the switch turns on at the rising edge of the clock. So, that is why it is called trailing edge modulation. Okay. But in this control, it can be shown, in fact, we are going to consider in lecture number 23 that this current loop will be unstable when duty ratio is greater than 0.5. In fact, the overall system can be unstable when when you go for outer closed loop, then it can be unstable even smaller than 0.5. That means it may be unstable around 0.45 or so. Okay. So, this is called peak current mode control. So, this is stable when duty ratio is less than 0.5. Now, there is another current mode control which is valley current mode control. So, how does it look like? In valley current mode control, if you draw the waveform, okay. So, same if you draw. So, we have a switching frequency clock and this on, then it is again on like this. So, this is the edge of the switching clock, and here the reference current, if this is the reference current is, let us say this one is my I ref. So, inductor current start falling, then goes up, again it start falling like this. So, this is our valley inductor current. Okay. So, in this, this is my inductor current, this is my reference current. So, in this case it can be shown that the current loop will be unstable for duty ratio less than 0.5. That means, and this is leading edge PWM, because here the switch turns off at the rising edge of the switching clock and it turns on when the comparator actually reaches, that means inductor current touches the reference current. Okay. So, that means we have two solutions, peak current mode control and the valley current mode control. Peak current mode control will be useful for low duty ratio operation because the current loop is stable, and the valley current mode control can be considered for high duty ratio operation when it will be stable. But if you just interchange, that means for high duty ratio peak current mode control, then what will be the scenario, and the low duty ratio if you go for valley current mode control, then it will be unstable. So, how does it look like and how to stabilize, that we are going to see. Now, in most of the many applications, because we are talking about low voltage high current application where the input voltage is 12 volt and the output voltage is 1 volt, and this is typically for voltage regulator module, even for portable application, where we generally consider peak current mode control, where we have a current reference and this is the inductor current waveform. Now, if you are going for high switching frequency, let us say 1 by 12, that means what is our typical duty ratio? T will be 1 by 12, because we know that okay. So, what is our duty ratio? It is nothing but our V0 nominal by V in. So, in this condition, like input voltage is 12 volt and output is 1 volt. So, it will be 1 by 12. Okay. So, it is roughly around 0.083. Okay. Now, if we go for high switching frequency, let us say we want to operate FSW to be 1 megahertz, then what is our switching period? It is 1 microsecond, right? Then what will be our on time? So, our on time will be D into T SW, and in this case it will be roughly 83 nanosecond, and this is too small. Okay. That means peak current mode control, we saw the stable current loop, but what about on time and delay? That means for low duty ratio operation, 83 nanosecond is my total on time. Okay. And during this 83 nanosecond, we will see what are the sequence of event that will happen within this 83 nanosecond, whether it is possible to complete all this sequence or not. So, if we go for peak current mode control, in fact, if you consider the outer voltage loop, then we have a current controller, and here it will be minus, it should be plus, because when it hit the peak current, then the comparator become high and it will reset. Okay. So, in this sense inductor current, suppose if you are sensing the inductor current, now what we want to discuss here, we saw for this case the on time is around 83 nanosecond, and that too for 1 megahertz switching frequency. Imagine what will happen if you go for 10 megahertz switching frequency, then your on time will be 8.3 nanosecond. So, 83 nanosecond you have to complete this computation because it is peak current mode control. So, that means what I am saying that you have you have this peak current reference and your inductor current has to reach, that means a very low duty ratio operation, it is like this, okay, very low duty ratio operation. So, it is difficult, that means your comparator has to finish the comparison, then error amplifier has to finish, the controller has to finish the computation. That means I will say there will be some delay into this. That means if you consider the delay, the sources of delay, one is the comparator delay, this is a huge delay, the maximum delay. Then the driver delay, because this will go to the gate driver which will actually turn on and off the MOSFET, and other delay may be the delay due to the compensator delay and so on. So, this delay can be, total delay can be even larger than the on time. That means you cannot operate or you cannot implement peak current mode control for low duty ratio operation because of the constraint on the on time, the total delay, that ratio. That means you have a very little time to compute. Then what is the solution? That means we cannot use any comparator action during the on time. It is simply may not be possible to implement. So, what is the solution? Is the valley current mode control. In valley current mode control, you have a long time. That means if you take the waveform, okay, then this is our valley current reference. Okay. Now, if you take the inductor current have a large time like this and suddenly go up, then again go down. That means you have a huge time, the off time is quite large. This is my off time, okay. This is quite large and this is my total time, that means this is my time period, switching period, okay. So, the off time is pretty large compared to the switching period. As a result, you will get sufficient time to compute this comparator and other thing because you have a huge time. But what is that means total delay is much lower than the off time, but the current loop is unstable for D because we have seen that, and you will see even using some current loop equation we can show that it is unstable for D greater less than 0.5. That means this control technique cannot be implemented because for low duty ratio operation, because the instability problem, the stability problem, current loop stability problem, even though you put a very high compensating ramp, still you have a problem because that will make the whole system slower, okay. Then what is the solution? So, I will show you a scenario in a boost converter under valley current mode control, okay. So, under valley current mode control, if duty ratio is smaller than 0.5, it is just 0.44, and this is the experimental result where the switching frequency is 500 kilohertz and input voltage is 7.5 volt. So, you will see when you talk about unstable current loop, now our question will come, then what does it mean? Unstable current loop means whether the current will go to infinity or it will look something else. So, this is one of the possible scenario. You see, these are our switching clock, this is our FSW in the experimental waveform, these are the switching clock, okay. So, this comes like this is our switching clock and these are the edges. That means our actual switching frequency is 500 kilohertz which corresponds to 2 microsecond, and you can see that the 4 microsecond is the division. So, this division is 4 microsecond, okay. But actual current waveform does not look like it is operating under 500 kilohertz because the ripple is quite large, and this is because of instability of the current loop, and this has to be analyzed using nonlinear dynamics. I mean, it is nonlinear dynamic, that means if the current loop become unstable, then what kind of nature, what is the nature of the current loop, that can be analyzed using nonlinear dynamics. So, this is not the part of this course, but it is clear from the power spectral that the current loop, because of instability, the ripple current is quite large and it will significantly increase the RMS conduction loss and your efficiency can degrade, and also you have subharmonic content because this is 250 kilohertz is the division. So, you will have a subharmonic component other than the switching frequency, that means lower frequency, and it will make your it will create a problem for the input filter design. Similarly, if you take a peak current mode control and if your duty ratio is greater than 0.5, because it is the case, it is just 0.6, and you see the same problem, the clock is here, it is a switching clock, it is our FSW and it is of 2 microsecond because the switching frequency is 500 kilohertz. Okay, and you will see the waveform of this inductor current does not look like it is repeating in the same frequency of 500 kilohertz because it is it has drastically increased, and again this can be analyzed using nonlinear dynamics, but it is evident that the ripple current is quite large and it will significantly increase the conduction loss, and in fact it will lead, actually because of this high current ripple, the output voltage ripple will be significantly large and it will actually go beyond the ripples, the output voltage actual ripple will go beyond the ripple specification. So, this is simply not acceptable. Then what is the solution? Now, if we add a compensating ramp, so this is our compensating ramp which is either added with the inductor current or subtracted from the reference current, then you can make the whole system stable even for a wide high duty ratio operation. But this ramp compensation, when you go for current mode control, you will see as you add more and more ramp, the current loop, whatever benefit we will get using current mode control, we are trying to separate the double pole by 2 first order pole by widely separating them. But once you add more and more compensating ramp, then those 2 poles come to close to each other and it will slowly tend to become like a voltage mode control. So, the all benefit of current mode control will be lost. So, if you go for a wide duty ratio operation, you need to increase the ramp slope, and as a result the major benefit or the advantage of current mode control may be lost. So, that means even if we introduce this ramp, this will also reduce the DC gain and will go when you go to current mode control. As a result, the DC gain will be decreased, so the closed loop bandwidth will get reduced, okay, and it can also affect the steady state error. So, now we need to find out solution. So, these are the problem using fixed frequency control when you go for a wide duty ratio operation, whether it is a very low duty ratio, whether it is a very high duty ratio, or whether it is a wide duty ratio operation. What is the solution? So, now this is the constant on time control. This is constant on time control, and we have discussed in week 2. In the week 2, what we have discussed, that valley current mode. So, this is analogous to valley current mode control, where we are controlling the valley current, but here time period is not constant, here on time is constant. And we will see in lecture number 23 that in this control there is no stability problem in the current loop. That means the current loop will be inherently stable for the wide duty ratio range, there is no problem. So, that means you can use this technique for a wide duty ratio operation. Now, when coming back to our original problem, that means low duty ratio operation. So, if you want to achieve this low duty ratio operation converter, so you simply use a constant on time control. So, this is like on time. Since this on time is fixed by a timer, you do not need to make any comparator condition. That means there is no comparator action coming in this duration. So, it is feasible even for a very small on time. So, for high frequency application, this can be used. Whereas, in this time, like when you are talking about the valley current, which this is the IREF. So, this valley current we are getting a large off time, and then this is sufficient to complete the comparator comparison, right, and then compensator calculation, everything is feasible because the time is quite large. And here it makes sure that it is stable. So, that is why in many commercial products, in fact there are many commercial products are coming for low duty ratio 12 volt to 1 volt operation and also multi-phase control. It is slowly shifting to constant on time current mode control and it has become a very popular control technique for low duty ratio operation. If you go for high duty ratio operation, then you can also implement, because you want to operate peak current mode control. Suppose you want to maintain the peak current, and this is particularly useful for LED driver. Many commercial products they use LED driver using constant off time, and the constant off time, if your duty ratio is higher than an entire duty ratio range, the constant off time is also perfectly stable, that we are going to see. So you can implement this logic for peak current mode control without any stability problem. That means we can solve this wide duty ratio operation by using either of this technique. So this is our constant off time control, constant off time current mode control. This is perfectly stable for the entire duty ratio range. So if you, whether you want to, and this is analogous to peak current mode control. This is actually peak current mode control, but here our switching frequency is varying. So off time is fixed. In our traditional peak current mode control, the time period is fixed. Okay. That means that's why this variable frequency control is very powerful in many commercial products they are coming now. Okay. The next, another very attractive solution is the power factor correction boost converter, because we need to achieve unity power factor for full wave rectifier. Like particularly this is useful if you go to battery charger application, adapter application, many application where your input is AC and you need to achieve a regulated output voltage. So what people use is in most of the commercial product they use a full wave rectifier, though now people are shifting towards totem pole PFC, but here it is a traditional PFC where we have a full wave rectifier followed by a boost converter, and here the objective of the control objective is to maintain the average value of this inductor current in such a way so that the input current actually follow the output current. That means there should not be any phase shift, so that you can get unity power factor, right. So this boost converter will virtually operate in a way, so it will look like an equivalent resistive load across the full wave rectifier, so that your input and output, input voltage and input current, they will be in phase. And also you need to achieve low total harmonic distortion, because in peak, because the duty ratio will widely vary, because your rectified voltage is varying like from 0 to this volt, and you need to boost this voltage from very low voltage close to 0 to a peak voltage. So this peak voltage, if it is 230 volt RMS, then you can calculate peak voltage, which will roughly come around 320 volt. Okay. So this peak voltage, and you want to achieve this output voltage roughly 380 to 400 volt DC. So DC, that means you need a very high step up for a wide range of input voltage variation. That means duty ratio is varying almost from 0 to 100%. And in such cases, you cannot use either a peak current mode or valley current mode, and many control use traditional average current mode control. Again, that there are bandwidth issue in average current mode control, and we will discuss in the subsequent lecture the loop interaction in average current mode control. But if you want to use a high bandwidth stable current control, average current control technique, then one of the way is to use a constant on time. And if you operate in critical conduction mode, then inductor current average can be tracked very perfectly if you set the on time just twice L by P out. This is the output power, this is the output power, and this is the RMS voltage of the input. So if you use this constant on time control using critical conduction mode, then if you choose this properly, even you do not need any other control, just on time this, and then you can actually achieve very nice unity power factor. And since this control has no stability problem for wide range of duty ratio, so you can perfectly you can reduce the THD. So that means you will get low THD because there is no distortion due to the current loop instability, as well as you will get unity power factor, okay. So this is a very popular technique, constant on time, in your PFC boost converter particularly. It can be also applied for continuous conduction mode as well, CCM boost, and as well as critical conduction mode boost, okay. So this motivates us, this variable frequency control is very powerful, even now they are becoming very popular in commercial product. The another aspect that I want to discuss, that in most of the fixed frequency control design, in fact the design part will come later, but today I want to show you, if you can develop the model of the control to output transfer function and the controller and modulator gain, then if you want to design this compensator, so generally our compensators are designed by considering what? Small signal model, and we will discuss in subsequent lecture. These small signal models are valid when the crossover frequency, or basically the control bandwidth, is set roughly 1/10 of the switching frequency for a buck converter, and for a boost converter it is the minimum of FSW by 10, right up plane 0 frequency by 5, and will come when you go to the boost converter design under voltage mode. All this will verify using small signal model as well as switch simulation. But just to talk about, the design of voltage mode control is carried out using transfer function, using small signal model, where the model validation, the validity of the model pose a constraint on the crossover frequency. Okay, so now we want to show a simulation case study. That means what are the model limits? So let us go to the MATLAB simulation. So here we want to consider first that we are going to talk about a step down load transient, okay, step down load transient, and I will explain in subsequent lecture all this design criteria, MATLAB code, but for today just for sake of comparison I am just running this. It is originally the inductor current, so is 20 ampere, then it undergoes a load step transient of the step size of minus 10 ampere. So let us run. Here it will ask for the bandwidth. Suppose you set the bandwidth of 50 kilohertz, and then in this design it will ask for phase margin 60 dB, so sorry 60 degree phase margin. Then we want to match this model. So we want to match this model. So we want to run this simulation, and I want to show you that once you go for this, so you will find the blue color trace. Okay, I think we should use a different color. Let us use another color which is red, and we can use this plot command here, so that we can use this plot command here. Okay, so it is like blue. Okay, now let us run this simulation. So I want to show you, first thing is that, okay, the red one is the actual switch simulation which is obtained by actual switching converter, and the blue one the response we got from small signal model. That means this blue signal is coming from small signal model AC analysis, and then we added offset DC, and now the total simulation result I am showing, the model response coming from the small signal model is accurately captured. I mean, it is capturing the behavior of the actual switch simulation. If you go, they are more or less capturing the behavior of the actual switch simulation. So you can predict using small signal model what will be my overshoot, undershoot, and so on. Now suppose in this case, if we want to increase the bandwidth, let us say we set 1/10 of the switching frequency. Suppose we want to go for 1/5 of the switching frequency. So 500 kilohertz is my switching frequency. If I go for the crossover frequency is to 100 kilohertz, and then if we design, if we again run the converter, I want to show you that whether the response can be captured or not. So if you check the response, it turns out that your model is unable to capture the behavior of the actual switching converter. That means there is a significant deviation between the predicted model obtained from small signal model, which is the blue color, and the actual switch simulation coming from the actual DC-DC converter. That means that's why what we talked about, that means our original discussion, that our model is limited to roughly 110. That's why in most of the commercial product our small signal model is designed for 1/10 up to 1/10 of the switching frequency. But it is a switching converter, you can improve the performance, but you should not use a linear model, otherwise you cannot predict. So we have shown the case study and we have discussed about small signal based voltage mode design, okay, and we identified the model limit, okay. Now what does it mean? That means if you go back, the slower bandwidth is due to the validity of the small signal model. That means whatever bandwidth we are setting in the closed loop, we want to make sure that our model is valid. That's why the bandwidth and all this frequency response comes into picture when we can get a linear model, right, and that is valid for 1/10 of the switching frequency. So we are getting slower bandwidth, okay. The slower control bandwidth attenuate, that means now if you go back here, so since our control bandwidth is slow, which is limited to control bandwidth is 1/10 of the switching frequency, so this controller bandwidth is slow and it will try to attenuate the ripple information which is coming from the loop. That means your actual output voltage, you should have some ripple, right, some voltage ripple. So this will be attenuated here, it will be attenuated here, because your controller will act like a low pass filter due to because its bandwidth is small. So that means you are losing the ripple information in the controller, and that's why our performance is limited, and the end result is a slower transient performance, okay. Now if we want to incorporate the ripple information into the controller, can we improve the transient performance? So that means what are the solution? Because this was our earlier example I have shown, right. So one of the option is that we go for ripple based control. That means in the control method we want to inherently retain the ripple information of the output voltage, okay. And another approach we will also show some result test cases is a large signal based design. We still can continue the pulse width modulation technique, voltage mode control, no variable frequency control, but in the process of controller design we incorporate ripple information. That means we are not making this controller or the bandwidth slower, because there is no bandwidth concept, because here we want to take the nonlinear model where we want to retain the ripple information. So if we can do that, then we can push the performance up to the physical limit and go beyond the conventional notion of control bandwidth. So first thing I want to show ripple based control. So constant on time control and constant off time control and the hysteresis control, and we will discuss in the subsequent class all these control technique. But we want to show a ripple based. So what are the structure? In the ripple based control, the output voltage is directly compared with the reference voltage, and the comparator output goes to the modulator, constant on time modulator. So here there is no compensator, right. So you are getting the full output voltage with ripple information. Similarly, the constant off time, we can retain the output voltage ripple information and we can just change the modulator here, okay. And the third one is the hysteresis control, where we can retain the ripple information directly, because the hysteresis directly work on the ripple of the voltage or current depending upon what kind of hysteresis control you are implementing. So I want to show you one case study, the voltage mode control versus ripple based control. So let us go back to our MATLAB case study. So if you go back, on top of this, that means we are going back to our 50 kilohertz bandwidth, because we know the model is valid for small signal based design, and we want to simulate our converter response, and this response is coming, we have some overshoot undershoot in the output voltage, and this is matching perfectly. So this is somewhat the achievable bandwidth from the closed loop control using small signal based design. Now suppose we want to incorporate constant on time control, because I have a constant on time. So I want to incorporate, and I am using a black color. So if you go to constant on time VMC, so this is the block diagram. here, because we have already shown the block diagram for voltage mode control, in constant on time control we are just taking the output voltage and the reference voltage, and if you go inside they are compared using a comparator. This is a comparator. Okay. So this is, that means the direct control, and this is the whole block is our constant on time modulator, because we have discussed we will be discussing in the subsequent lecture that you need to incorporate a minimum of time so that it will not collapse. Okay. So all this part will be discussed, but in this simulation we want to run this simulation and check how does the response look like when you use a constant on time control. Okay. So we are using a black trace to show the response due to the constant on time, and already we have used a voltage mode control fixed frequency. Now if you see the response, the black color is the one which you obtained from ripple based control, and if you go as if it is very fast, I mean extremely fast, and if you go to the inductor current waveform, so I want to show you that. So the red one is coming from our small signal model like a voltage mode fixed frequency control, and the black one is coming from our constant on time control, and you can see it is responding very fast and it is reaching steady state much faster. Okay. Whereas because of the small signal based design, so our overshoot during the step down transient is pretty much higher. Okay. So the constant on time control, since it directly work on the ripple based approach, so it can be really fast response, very fast response can be achieved. Okay. So now we are going back to our original discussion. So that means the ripple based control is much faster. The ripple based control is much faster than small signal based voltage mode control design. Okay. Because why you are saying, even we will see if you go for large signal based voltage mode control design, even it can be faster than the ripple based control, but we are not discussing, and that is one of the major theme of this course. At the end we will show the large signal based control can improve the performance drastically. Okay. But now we are showing just small signal based approach because of the bandwidth limit. Okay. So I will just want to show a few experimental case study. This is the constant on time digital current mode control, where in the constant on time we have discussed that you need to put a minimum of time. Okay. That means the constant of time on time, it can be shown, and it is well reported, it suffers from poor transient performance when you go for step up transient. Okay. And people actually use a adaptation of on time in order to improve that, but if you use a traditional constant on time control, your step up transient will be penalized, but the step down transient is excellent. If you go for constant off time control, then the step up performance is very nice, but the step down will be penalized because you need to incorporate a minimum on time. Okay. And that we will discuss in the subsequent lecture. Why do you need to put a minimum off time for constant on time control and the minimum on time for constant off time control. Okay. Because otherwise it will collapse. Then the ripple based control, if you actually we have proposed that hybrid digital current mode control, where you take the best of constant on time and off time just by a simple modification of the clocked signal without changing the hardware. So it is achieved, it is we could retain the very fast transient response. Now incorporating ripple information in controller tuning. As I said that you can design the controller by considering the current ripple. I mean, we are not going to restrict the small signal model, that is option 2, and if you do that, then you can actually, this is the small signal based design that we have discussed using small signal based design, and this is the large signal based design, the same converter by using a large signal based approach, because in traditional control during transient the duty ratio variation has to be small, otherwise the small signal model is not valid and that limit the performance. But in large signal based control you allow the duty ratio to saturate, so that it will sleeve up and sleeve down, quickly come down in one switching action, and sometimes we call it as a time optimal control. It is the fastest control, and that is possible using our traditional PWM control by using a large signal based tuning method. Okay. So, now we have extended, that means this control technique can significantly improve the recovery time of this converter. So, here we are achieving almost 6 times faster response, and you can reduce the undershoot of the output voltage. You can see it is much higher, you can reduce. So, as a result, this also gives us a flexibility to reduce the further output capacitor value. So, you can in fact design a smaller output filter or output capacitor, so the power density can be increased. And it can be shown, if such frequent load transient happen, this second approach can even save power, or it can achieve higher efficiency, because the number of switching during this recovery process is much less compared to our traditional control. So, we will discuss this in detail in the lecture in the later part of this course, but we can use this for boost converter, and you can substantially, because the boost converter, when you design voltage mode control, even current mode control, we will see the current mode control, your bandwidth of this or crossover frequency will be limited to FRHP 0/3, and that makes the whole boost converter control response is very slow. But if you go for large signal based control, you can increase even 8 to 10 times faster. So, that boost converter we can, but the earlier was the current peak current was high. So, you can put a current limit and you still can achieve. So, a small signal design, it takes 72 microsecond for 2 microsecond time period, whereas all other approach that we have developed, it can really speed up the response. So, the bottom line is this, that large signal based tuning can be incorporated to improve the transient performance. So, the challenges, but what are the challenges is variable frequency. So, one we talked about constant on time control, right? We talked about constant on time, we talked about constant off time, and we talk about hysteresis, and we will take detailed comparison. All these are control. So, all these suffer from variable frequency operation. Then how can we regulate the switching frequency? That is why many of this technique is not used for nominal load condition, but now you can incorporate another loop, which is the frequency control loop. The frequency control loop, another loop, feedback loop. This loop is used to adjust the on time for this case, or off time for this case, or the hysteresis band for this case, such that your overall time period will reach close to the desired value. So, that means, but this frequency loop is much slower than control bandwidth, otherwise they will interact. So, it is much slower than the control bandwidth. So, the variation of the on time or off time or adaptation happen very slowly. But if you can implement, then you can achieve nearly regulated, you can regulate the switching frequency. And for these two technique, it is somewhat straightforward, because if you take the time to digital converter, that means time to digital converter. So, you can get the instantaneous time period, and you can create a feedback loop and compare with the desired value. So, let us say this is your actually on time which is instantaneous, and this is your desired. So, what you will do, this will be subtracted from your desired value, because these are all number, and then the error, then you create a map, a function, and that will generate, in case of constant on time, it will generate the on time adaptation. That means, it slowly adjust the on time in order to achieve the fixed switching frequency. It can also be used to adjust the off time, or it can be used to adjust the this particular hysteresis band. So, first two technique is easy, because your timer using a digital means, that is digitally assisted, that means the timer can be just a counter. So, you can just you can use a monoshot timer using digital, not in analog. Okay. Then you can just load this counter by by using this adaptive value by adaptation, right, and you can regulate the switching frequency. But the hysteresis control that we have to take seriously. If it is analog, it is not very easy, because it is analog, you have to implement and you have to voltage control that particular band. So, you need to take special care. So, in summary, variable control techniques are very helpful, okay, but it also comes with a price, that variable frequency operation. So, you need to incorporate a frequency loop, but now with the more growing towards digital control, actually this variable control you can, because in digital already have a digital platform. So, the frequency regulation loop can be simply that using a all digital PLL, simply a counter based approach can be used, and that will not take much of the resources, and that is how you can even adjust the switching frequency very effectively. So, the ripple based control motivating case study we have demonstrated, and now this also tells us that the current commercial products are coming up with more ripple based control, okay, because particularly for low duty ratio operation, if you go to multi-phase converter, most of the manufacturer or the vendors in current mode control, they are coming with constant on time control. The MATLAB case studies we have demonstrated, and we have also demonstrated few experimental case studies. So, with this I want to finish it here. Thank you very much.